So let me remind you where we were. Oh, sorry, maybe even before that. Today I'm so optimistic that I'm leaving the program on the screen. Anyway, so we have 2.5 categories, namely 2 categories and 1 soon-to-be made category. So the category of homomorphisms between polynomials, all of them have objects finite sets. So here the morphisms are homomorphisms between polynomials in the variables in the z's corresponding to some set A, and with targets at the z's corresponding to some set B. And the point is that this really corresponds to, or these polynomials represents elements in algebras, the Heisenberg algebra. The second category was the category of generating functions, and the morphism from A to B are the power series in the variables dual to A with coefficients polynomials in the variables in B. And these 2 categories are isomorphic, are the same, via the generating function map, which, and then if you check what the composition law is, so if you have 2 power series of this type and you want to compose them, then, so L composed with M, you do L followed by M, is you take L, you replace all the Latin letters in it by differentiations with respect to the Greek letters, and apply it to M, and then substitute all of these letters, Greek letters, to 0. So really it means that you pair the Latin letters here with the Greek letters here, and basically, on monomials at least, it means that the answer is non-zero if and only if the part of the monomial which is Latin here is equal to the part of the monomial which is Greek here. And then the pairing is the factorial of the power in the monomial, the exponent in the monomial. And then the third category is supposed to be a subcategory of this, and it's a tiny, tiny, tiny subcategory. So of all the power series, which is an uncountably infinite dimensional space, it's only those that are of the form a scalar times the exponential of a quadratic. And I made explicit what a quadratics are, so let me remind you. So it's quadratic in all of the relevant variables, namely in the Greek letters corresponding to A and the Latin letters corresponding to B. So it's linear, so Q is a certain sum of the form sum over I in A, J in B of Greek in A, in Greek I, Latin J, with coefficient Eij. Then there is 1/2 times Greek terms, and 1/2 times with coefficients a matrix Fij, and 1/2 Latin terms with coefficients a matrix Gij. Okay? And I said this is only half a category. Well, it's actually fully a category, but we only half understand it because we still don't know what is the composition law. I mean, we know the composition must correspond to that, but it's not at all obvious that composing 2 things of this form gives again a thing of that form. Okay. One further minor comment before we deal with the composition is the following. So notice that we exponentiate Q. To exponentiate something, right, I mean, what is e to the x? E to the x is sum x to the n divided by n factorial. this has to somehow converge. So in analysis, x has to be, well, actually e to the x always converges. But in general, in analysis, we say that power series converge when the parameter is small. I'll use the word small in an algebraic context as well. Okay? But what it means is that I've completed and allowed power series. Okay? So, so sort of a variable is small if power series in that variable are allowed. So this does not make sense inside polynomials in the variable x, but it does make sense inside power series in the variable x. So once you allow power series, it's as if you declare the variable to be small. So we need to exponentiate q. This term is small because it has a zeta in it, and zetas are small because I'm allowing power series in them. This term is super small, okay, because it has two zetas in it. But this term, as it stands, is not small, because the Latin letters aren't small. I mean, I only have polynomials in the Latin letters, okay? You could dream for a second of solving it by allowing power series in the Latin letter as well, So you could dream of solving it by allowing power series in the Latin letters as well, but then the composition will not be defined. Because then you will be, I mean, here the differential operators are polynomial, finitely many differentiations. If you'll allow infinitely many differentiations, you'll have convergence issues. You will not be in algebra anymore, okay? So that's not a good idea. So the solution is that the g, the coefficient, must be small. So what does it mean for the coefficient to be small? So really, my coefficient should not be the rational numbers. I'm pretending that it's the rational numbers, but it should be the rational numbers extended with some small parameter, for example, t. So when we talked about the Heisenberg algebra, we really allow the small parameter t. So where t is small. So really, all of these things should also be power series on yet another variable, t, or epsilon, or whatever, which is to be regarded as small, meaning where I allow power series in that variable. And in fact, if you look at our formulas for Rij was of like the g part. Rij had the g part, and the g part was small, so we're fine. Okay, now we need to compose two such things. So my strategy will be, well, I will, so okay, there are, I'm going to give you formulas for the answer. Okay? I could derive these formulas with pure algebra. Well, really differential equations, but sort of differential equations in the language of, I mean, it's the language of differential equations, but it's fully algebra because there's no analysis in the business, no actual analysis in the business. I mean, what I prefer is to develop some combinatorial intuition. So I'll try to develop some combinatorial intuition for how to compose such things. You may end up complaining that the combinatorial intuition is somehow incomplete, but it will give us formulas. Once we have formulas, we can test them. If the test succeeds, it becomes a technical issue, really. Something for technicians to work out how to prove it. Sorry, I view the world completely different than many other mathematicians. Okay? Anyway, so let's develop the intuition first of all. So, what does an element of the category GDO look like? So, I want to think of it as a coupon, a rectangle that has the inputs on the left, the outputs on the right. So in other words, Greek letters on the left, Latin letters on the right. And let me just indicate what are the Greek and the Latin letters. So really I should have an F here. And I'm writing F with two legs because F is quadratic, so it has zetas on both ends. Similarly, there should be a G facing to the right because G has Latin letters on both ends. Also, it has an E going from side to side. So this really stands for summation. It's EIJ and zeta I, ZJ. Okay? And finally, let's say up here I store omega. Okay? So omega is just a scalar. So it's just a coefficient. Okay? That's a bit of a lie. Because the quadratic part, Q, is exponentiated. So I don't just have a quadratic facing to the left, I have the exponential of a quadratic facing to the left. So really you should be thinking that F is not a single line going from left to left connecting zeta I and zeta j, but it's an infinite collection of such lines, or not quite an infinite collection, because let me remind you what is e to the x. E to the x is sum x to the n over n factorial. So really I mean a big linear combination in which the term with 7 parallel lines appears with coefficients 1 over 7 factorial. Likewise, G is not really a single line, but a bunch of lines. And likewise, E, the E term. But omega is just itself. Omega is just the coefficient, it's a scalar. Okay? So, in principle, I need to tell you how to compose it with another such coupon. Okay? But even before that, I want to understand something about the function e to the x, because I'm going to need some intuition about it. So e to the x is the true Hilbert Hotel. Or maybe not. Let's not argue about what is true and what is false. So I mean, you know the standard story about the Hilbert Hotel. I'll repeat it in a moment, but so maybe not true, let me just say the linear or the algebraic Hilbert Hotel. So, the story about the Hilbert Hotel is, so the Hilbert Hotel is a hotel with a countable number of rooms. So, if a new, and the fun thing about it is that even if it's full, you can make room for another guest, because you push all the guests one room to the right, and then the first room becomes empty. Okay? Or let me say differently, if you mark one room in the Hilbert Hotel, it remains empty. It remains the same as it was. If you occupy one room, if you cancel one room, it's still the Hilbert Hotel. Likewise, if infinitely many guests are already in, you can still bring infinitely many new guests in, because you just move every guest from whatever room they were in to the room with double the number, and then all the odd numbered rooms are empty, and you put your new infinitely many guests in there. I'll view it differently. If you mark each room, you know what, let's do that later, but first let's do the first property. So you see, what does it mean algebraically to mark a room? So and cancel it. So you take a bunch of rooms, you cancel one of them, you have fewer rooms. Okay? So if you do it to, say, a hotel with 4 rooms, you get you have 3 possibilities of getting a hotel with 4 possibilities of getting a hotel with 3 rooms, because you can mark any one of them. So, so really it's differentiation. And killing one x is differentiating with respect to x. So the derivative of e to the x is e to the x. So the Hilbert Hotel is unchanged if you occupy one room. Okay? And also, you know, if you take each room in the Hilbert Hotel and allow it to decide arbitrarily whether it's green or red. Namely, allow it to decide whether it's reserved for the red list of guests or for the green list of guests. So basically you replace every room, so you take e to the x and replace x by x1 plus x2, which really means, again, each room gets to decide what type of guest it goes to, type 1 or type 2. So you get e to the x1 plus x2, which is e to the x1, e to the x2, so you just got 2 copies of the Hilbert Hotel. You can do with them whatever you want. So that's something to keep in mind about exponentials. Let's see how it plays in a moment. Anyway, now I want to take 2 such things and compose them. So I have another such coupon with e's here and f's here, and again, each of them is a multiple, and g's here, and an omega here. But you know, I want to make this one, I want to make them 2 separate ones. So let's call this one omega 1, E1, F1, G1, omega 2, E2, F2, G2, and I want to compose them. And my dream is that the result will be omega E, F, G. Okay? Now, how does composition work? Composition works by taking a Latin letter here, converting it to a differentiation, differentiating the Greek letters here, which just means that you pick one of the Greek letters here, and you connect them. And you pair them. The 2 cancel each other. From now on, they cannot be used again. Right? So in doing this, we cancelled a pair of Latin and Greek letters, and we remove 1 copy of G. But if you remove 1 copy of G, nothing changes. That's the Hilbert Hotel property. Okay? So we still have exactly the same reservoir of G's here, and exactly the same reservoirs of F's here. But I have the other side of that G. Or in other words, this Z really was some Zi, and it came with coefficient Gij, and then there is the Zj on the other side. that Zj on the other side might be paired with a zeta that comes from an E. Right? So basically what I end up doing is I end up constructing graphs by that basically zigzag between, or not zigzag, alternate between, doing a G, going through an F, going through another G, going through another F, then going through an E and coming out, or something like that. Okay? So let's count these graphs, or let's see what would be the contribution in the output to each such possible graph. So for example, what will be the E in the output? Namely, if I start on the left, with what coefficients am I going to come out in the right? On the right. So if I start with some Greek letter here, well, it's going to appear within a quadratic with some Latin letter on the right, and what would be the coefficient? So how can I start on the left and end on the right? Well, there are infinitely many possibilities. So one possibility is to start here, right? Sorry, I mean, how can I get an E term in the output? So one possibility is to start here, go through E1, now I'm here, now pair this Z with a zeta which belongs to E2, and then I come out, and nothing gets glued on the right, so once I'm out, I'm out. So, therefore, one contribution to E is multiplying the matrix E1 with the matrix E2. But another contribution is I could have started here, gone to this Z. This Z could have been paired with a zeta corresponding to an F. Then I would be here. Then I would connect the other side of this F to a G. Then the other side of this G would be connected to an E, and I'd be coming out. So the next contribution is E1 times F2 times G1 times E2. But then I could have done this thing twice. So I would get a contribution. And by the way, each time I compute such a contribution, in principle, I remove one copy of F or one copy of G, but that doesn't change anything. So the next possibility is I start here, go through an F, go through a G, go through another F, go through another G, and come out with this E. So the next contribution will be E1, F2, G1, F2, G1, E2, and so on. So really I get E1, sum over R goes from 0 to infinity of F2, G1 to the power R, multiplied by E2. This is a geometric series of matrices, but it's still a geometric series. The sum is E1 and then identity minus F2 G1 inverse E2, and that's my conjectured formula for E. So if you want, call it a conjecture. Once you get used to these things, you realize that it's not a conjecture. But anyway. Now let's find what F could be. So I enter from the left. How could I come back out on the left? Okay? So right, that's what F does. If I enter on the left, how will I come out on the left? So I enter on the left. one possibility is to just exit with the f1s that I have. Another possibility is to go through E1 to here, then loop between F2 and G1 a number of times, and then come back with E. Okay? So in other words, one of the F's at the end will be, instead of connecting to a G, will connect back again to an E, and I'll be heading out. So this will be E1 identity minus F2 G1 inverse. This just means that you loop, you do the FG loop an arbitrary number of times, and then you exit with an E1 transpose. In fact, if you look at it. Okay. No, what am I doing? Yeah, sorry. Yeah, sorry, that's fine. Right. Likewise, what's G? So if I enter, so G is enter from the right and exit from the right. So if I enter from the right, I can exit immediately via G2. So G will be G2 plus plus I can go with E2, loop through G1 F2, and eventually exit with E2. So the result is E2 transpose 1 minus F2 G1 inverse E1. And here I was confused about the order in which G1 and F1 goes. It's actually the opposite order. You first, if you do an E, you first do what? If you do an E, you first do, if you do an E, maybe the formulas I wrote on my notes are wrong. Sorry. If you do an E, then you do an F. Yeah, so sorry, so it was wrong as it was right as it was. But this one is wrong. So this is G1 F2. So you do an E backwards, then you do G's and F's. Yeah. Okay. And finally, what's the constant term? So you see, I didn't really count all the possible contractions or all the possible trips. There is another type of trips, yes?
Oh, just for the formula for G, don't we also want to follow E2 back out to the right?
Yeah, you're right, it's E2. Right, sorry. So there is yet another type. And the other type is closed loops. So I could contract a G with an F, and then the F again with another G, and then with another F, with another G, and so on. And then the last thing could be connected to the initial thing. Okay? In general, when you contract the index of a matrix with itself, that's taking the trace, right? If you have a matrix Mij and you sum over all ways of connecting of identifying I and J, then this is the trace of that matrix. So here we will have the sum as R goes from 0 to infinity of what will it be? The trace of G1 F2 to the power R. And and now I have to tell you about a principle that that deserves an explanation, but I will not explain right now. And this is, so you see, really here we created a diagram where you have F and then G and then F and then G and then F and so on, and then G and then F and then G. And the principle is that whenever you have such a diagram, you have to divide it. You have to divide a corresponding term by the order of the automorphism group of this diagram. If you've seen physics, it appears in physics in many places. If you haven't, it requires a justification, but I'm putting it on hold. Okay? So anyway, if you have a cycle of length r, it has two r symmetries, because you can flip it over and you can rotate it r times. So the coefficient here should be 1 over 2r. And in fact, in all of these, in all of the previous computation, so the previous computation, for example, computation of E involved starting with an E and then zigzagging and then coming out, but that has no symmetries. So in all of the previous things, there were no symmetries to divide by, and here there is. Anyway, what is this? So this is the power series for, I think, log, or log of 1/2. No, the power series of, oh, sorry, pull the 2 out, and then it's the power series for minus the logarithm. So this is minus 1/2 the logarithm, the trace of the logarithm, minus 1/2 the trace of the logarithm of 1 minus G1 F2, and the trace of the sorry, is it the trace of the logarithm or the logarithm of the trace? It's the it's the trace of the logarithm. So expand this as a power series. You will get this power series, and you put the trace every place. And then the trace of the logarithm of a matrix is the logarithm of its determinant. So think like eigenvalues. So the trace is the sum of the eigenvalues, the determinant is the product. So the sum of the logarithms of the eigenvalues is the logarithm of the product of the eigenvalues. So this is minus 1/2 the logarithm of 1 minus G1 F2. And I'm running out of space, so I'm not sure where to continue. Oh, sorry. Yeah, well, so okay, I'll just continue here. So, but this is just the logarithm of, so this is the logarithm of 1 minus, sorry. Yeah, this is the, oh, I'm messing up. This is the logarithm of 1 minus G1 F2 to the power minus 1/2. And what I did here was not computing omega. I mean, I was computing a contribution to omega, one specific contribution to omega. So this is, I don't know what should I call it, contribution to omega. So now what is omega? So omega, namely the scalar coefficient here, is the scalar coefficient from here times the scalar coefficient from there times the new contribution. Sorry, I forgot the determinant here. No, this is the log of the determinant. And this is, again, log of the determinant to the power minus 1/2. So I have the contribution from here, the contribution from here, and the new thing. But the new thing gets exponentiated. I don't just get, if I do this process one time, I get this contribution. But then I might still have chords left here and here. So I might do it again and again and again. So I really get the exponential of this. The exponential of this is just the determinant of 1 minus G1 F2 to the power negative 1/2. Yeah, oops, I don't know what to tell you. This is, this requires justification. But as I said, let's verify it. Yes?
Quick question about,
Yeah.
so for the formula for G,
Yeah.
why are you taking E transpose?
Well, because I'm going backwards, and you have to think a little bit what it means in terms of the indices. No, I'll keep it this way. Yeah, maybe I'm doing wrong, but I mean, if you think about the matrix multiplications that occur, that this really represents, this is the right thing to do. I'm not sure if I have the the energy to go through it in full detail, or or maybe even the need. So. Yeah, so take it as intuition that needs to be justified, and that the justification takes a few hours. Okay, takes a lot of detailed work. I'm also not worrying too much. I didn't worry about combinatorial factors. The only place I worried is where it mattered, namely here. But all the combinatorial factors work out. Yeah, I mean, like, one could develop a theory of such things, but that's a huge amount of effort. So and one needs to know this. Well, okay, I don't know what to say. I'll just verify. And then later, we will also prove this algebraically. So at the moment, it's a combinatorial intuition which leads to formulas that we can verify, and later we will find alternative proofs. Anyway, yeah. So again, let me just verify it. So unfortunately, the verification starts with something annoying. So Mathematica doesn't deal with series very well. So for example, let's compute e to the a plus b times x and turn it into a series in x around x equals 0 and to the power x cubed. So, well, you actually get the right answer. 1 plus a plus b x. Well, I mean, you get what's written here, and you can easily see that you know it's correct. However, if you try to expand this series, Mathematica doesn't do anything. Mathematica, for some reason, doesn't expand series well. So, I mean, I can tell you what is the reason. The reason is that series have a special representation, and whoever implemented expand did not bother to look into this, to expand things with this special representation. The special representation, so if I look at SEER, this series here, in full form, then it's a series data, where the series is a series in the variable x near the point 0, and then the list of coefficients is a list. The first coefficient is 1, the second coefficient is a plus b, the third coefficient is the product, so times of the rational number 1 over 2 with the power of a plus b squared to the 2, and so on. And Mathematica expand doesn't look into series data. So I have to start the verification with a stupid hack. And the stupid hack is to unprotect series data. So series data is a built-in symbol. So you cannot change it before you unprotect it. It's protected. So I unprotect it, and then I say, if you see a series data and somebody tells you to expand it, then you apply the expand operation to the third term of series data. The third term is that list of coefficients. So once I execute this, after I've executed this, and then I run expand, now each coefficient gets expanded, which is what you would have wanted to have. Okay? Good. Now I define the dual of the variables. So the dual of p is pi. The dual of x is psi. The dual of pi is p, and the dual of psi is x. And then if I have a variable with a subscript, I take the dual by applying the dual to the variable name and keeping the subscript. So that's just technicalities. Oh my God. And then comes the composition. So So now comes the composition in the category of generating functions, right? I need to verify that the formulas over there correspond to compositions of generating functions. So first of all, I need to define how to compose generating functions. So, so suppose you have, so my notation for a morphism in the category is, it's blackboard G, subscript the domain, which is a finite set, arrow the target, which is again a finite set, and then with bracket and then L, where L is a power series. So, for example, here is a morphism from psi1 to x1, so really from 1 to 1, whose corresponding power series is written here. And here is a morphism from psi1 to x2, whose power series is written here. And this code here defines how to compose them. So once I've input this code, and I will explain in a moment how it works, I can compose things. And this is, we actually did exactly this example last time and got exactly the same output. So this will be a morphism from the Greeks of the first to the Latins of the second. So from psi1 to x2. And last time we checked that the corresponding generating series is this. Anyway, how does it work? So if I want to compose one generating series with another, first of all, I check that the dual of B1 is A2. And if this is the case, I make the following definition. If this is not the case, I just don't know what to do. So the program just doesn't tell you what to do. So if this is the case, I make the following definition. So what I do is, first of all, I take L1 and replace all the B variables. So replace all the variables corresponding to B1 with, I should have called this bar. You know, maybe I should just replace every time, I should have called this bar, because bar is the notation we used last time. So basically, I should replace every place I see a variable, I replace it with bar of that variable. And again, the point is to avoid confusions between, well, we mentioned it last time. So first of all, I take L1 and replace all the variables in B1 with bar of that variable. And then the same for L2. Then I multiply the two and expand. So now I have a big collection of monomials. And inside each of these monomials, I need to, every time I see bar of a Latin letter with some power, and then bar of a Greek, of the dual letter, with the same power, I replace it by p factorial. And after I do that, if any letters remain, I send them to 0, because I need complete pairings. And then I output a generating function from A1, so from the input of the first morphism to the output of the second morphism to B2 with output R. So it's a rather simple program, and it works. I'm out of time, so I can't really show you yet how to implement all the nonsense over there, but I'll just show you, this is the full implementation. You compute E1, you compute E2, you compute F1, compute FG, you compute all of these things, and then multiply the matrices and their inverses as the formula is written over there, and then you verify and everything works. I'll have to do it next time. So I think there is a colloquium here right now, so we actually can't go. You know, we have to stop. So see you next week. No, sorry, see you on Friday. Yeah. Okay.